Hello, here's a lesson to explain the last lesson of the computer organizational topic. So, here we have file extensions. We've already learned that computers understand ones and zeros. But how do the computers know what the ones and zeros are? That's why when you open up a document, we have a file type. Some documents have a file type that is universal across all computer systems. Some have file types that are very specific to the software. So for example, TXT, ASCII and Unicode will be read by all computers, where docx will only be read by a computer that has Microsoft Word on it. MP3s can be read across all computers, but WAVs can only be read by Windows and AAC can only be read by Apple. We have pictures. We have PNG, JPEGs, GIFs, BMPs and portable network graphics. So PNGs can be read by a lot of things. BMPs have a massive file type because they store everything as dots. GIFs are quite low quality and you probably see them for memes. JPEGs are what most standard cameras use unless you're shooting in camera raw. We have MP4s. They're the most common video type. However, you do have .mov and .wmv. WMV is Windows only. When the computer sees the file type, it knows how to interpret the ones and zeros and therefore what you see on your screen. Next, let's talk about letters. In the past, we had ASCII. ASCII is American Standard Code for Information Interchange, and it declared that we could have 8 bits in order to store letters. That meant, as you know from binary, that we had 127, not 28 as it says there, different letters that could be stored. That means if I wanted to store a Greek poem, I couldn't because there was not enough letters available and not enough different codes available. That means I had Unicode 8 was invented. That meant Unicode 8 was still 127, not 128 like it says there. And they also developed Unicode 16, which allows 16 different bits per character, which meant that we now had millions of characters to play with. Okay, not millions, thousands of characters to play with, rather than just 127, which means that we can store all of the alphabets around the world. So if I want to read a Greek poem in Greek, I can store it on my machine. If I want to read Korean in Korean letters, then I can see that. If I want to have Spanish letters or I want to have Romanian letters, when letters in the Latin alphabet that have extra parts, they can be stored. This is all thanks to the fact that we use Unicode rather than ASCII to now store our letters. Now let's take a look at pictures. Here is a picture of a cute little cow. You can see that the cow has got lots of colours, and if I take a closer look at the cow, he is made up of all dots. These dots are known as pixels. Each pixel has a colour code attached to the back of it, which says what colour it needs to be displayed as when it is on the screen. Colour values range from 1 bit to 24 bits. 1 bit is pure monochrome. The pixel is either black or the pixel is white, and we have no colour detail. We then have 24 bits. 24-bit colour allows us to store 60 million colour, and this is known as true colour because the human brain cannot effectively process more than 16 million colours. So if we were to store anything above 16 million colours, it would be pointless waste of space in our machines. You have to be able to calculate the size of an image based on the image and the information that is given to you. So if we say that my cow picture, although it's clearly not, was 10 inches by 10 inches, understand that it was 24-bit colours. It is true colour. We want to see all of the pictures on the cow. I would also have to know the dots per inch. And I forgot about the dots per inch. So then I'm just going to get rid of the start of my calculation. And I'm going to add the dots per inch information. The dots per inch is the number of pixels that are in 1 inch of the screen. So if we take the top left inch squared, we could have 600 dpi in there. That means that there's 600 dots in that corner. Now we can do the calculation. 10 by 10, and I didn't need a calculator for this bit, is 100. I then multiply this by 600. And my maths is awful, so I needed a calculator. You'll just have to wait. So that gives me 60,000. Then I times it by 24. That's the number of bits that I am using to store each colour, which gives me 1,444,000 bits that is required to store this picture. Now you think this is a lot, but this is bits, so it's single ones and zeros. The first thing we need to do is divide it by 8 in order to get it into bytes. So that gives me 180,000 bytes. That's still way too big to be talking about a picture. So the next thing I do is I divide it by 1024 in order to get it into kilobytes. That means we have 175 kilobytes, so it's actually quite a small picture. If this was bigger than 1024, I'd have to divide it again in order to get into megabytes. And if that was still bigger than 1024, I'd have to divide it again in order to get it into gigabytes. So anytime it is over 1024, you divide it. Now let's talk about sound. MP3 is an example of a lossy compression. What this means is it takes exploitations in the human hearing. It plots the frequencies that the human ears can hear, which is this bit in the middle. It chops off the top, chops off the bottom, and performs some other calculation that means that it can understand where the human ear can fill in the blanks, and it cuts the file size to create an MP3. It is lossy compression. Data is lost in the process of producing an MP3. We then have WAVs. WAVs are lots of different waves, and a calculation is used in order to squash the data in the WAV. It is a lossless compression. No data is lost when you create a WAV file. You were never asked anything more technical than the difference between a MP3 and a WAV, MP3 being lossy and WAV being lossless compression. You might be asking yourself, what about video? Well, video and TV shows are just lots of different still pictures on screen shown at you in very quick succession, usually 12 or 24 frames per second. I can't remember which one is European and which one is American. But if you count the number of seconds in your TV show or movie, and you know the number of frames per second, and you know the size of the images on the screen, all you need to do is further add to your calculation. So I know that the cow is 175 kilobytes. So then if I do 12 by the number of seconds and then by 175, that will give me the size of my video.